Greetings, gang, and welcome to Chapter 4, or Newton's Second Law. Now, last time we talked a little bit about the rate at which objects accelerate as they fall. And we could very clearly see that because the paper is affected by air resistance, not the same way that the pen is, they fall at different rates. Until we remove the air resistance from the equation and they fall together. So both objects were dropped from rest with an initial velocity of 0, right? After falling, they hit the ground at the same time. So what do they have in common? Obviously, their beginning heights. When they hit the ground, they have the same velocity, right? And also, that means that their acceleration toward the ground had to be the same, right? Now, what caused them to accelerate? Gravity caused both of these things to accelerate as they fell, right? Now, what I really wanted to do was to have a big tub of sand so that I could take these two objects and drop them into the sand. And you could very clearly see that if I took some heavy object like a stone or a chunk of metal or something like that, and I dropped it into a big bucket of sand, that it would splash out and make a crater. I've included a link to a sand crater demonstration video by NASA, and if you haven't seen it already, this is a good time to go and have a look. In any case, once you've done that, you could pretty obviously tell that if you took a massive object and dropped it into the sand, that it would make a crater. But if you took a wadded up piece of paper, it probably wouldn't make as much of a crater, right? It wouldn't be able to displace nearly as much of the sand. Now, why is that? What does a steel ball the same size as a wadded up piece of paper have more of? Obviously, the steel ball has more mass, right? You can also say it has greater density, blah, blah, blah. But basically, it's the same thing, right? They're the same size, but the steel ball has more mass. Now, if you took the steel ball and you dropped it, it would make a certain size crater. But also, if you took the steel ball and you threw it as hard as you could, you would create a larger crater, right? Why? Well, that's because the force on impact obviously is going to depend upon the mass of the object that hits the sand to make a crater, right? But also, if you accelerate it more, right, by throwing it down instead of just dropping it and letting gravity take it, obviously there's going to be a greater impact force and make a bigger crater. Thus, the force exerted on the sand depends upon the mass of the object and how quickly it is accelerated, right? We call this Newton's second law of motion, also known as force equals mass times acceleration. So just like the falling paper and steel ball, forces cause objects to accelerate. And if we take the simple case of an object that's being accelerated by gravity, the force of gravity, or the weight on an object, is the mass of the object times the acceleration due to gravity. This is our 9.81 meters per second squared. Now, what are the units of a force? Well, the unit of a force is a newton. But what is a newton? What does it represent? Well, the unit of mass is kilograms, and the unit of acceleration, if you remember, is meters per second squared. Thus, a newton, or the unit of force, is kilograms times meters per second squared. But how come our weights aren't in newtons? Why is it that if we get on a bathroom scale or something like that, it usually, actually in this country, it usually reads pounds, but in most of the civilized world, it says something like kilograms? Well, that goes something like this. So let's say you've got your bathroom scale here, right? And you decide you want to stand on it. Now, which way is your weight pushing on the scale? Downward, right? And that means the scale is going to push backward up on you, right? it's going to hold you up because you are neither accelerating into space nor accelerating through the floor. The scale is holding you up. And so, I'm sorry, this is your weight. So your weight, or mass times gravity, has to be equal in magnitude and opposite direction to the normal force, so the force that you make contact with the scale. You make in contact with the scale, excuse me. Now, one of the interesting caveats to this, force equals mass times acceleration. If you want to try to determine your mass, if we divided both sides of this equation by the acceleration, what do we get? We get force over acceleration equals mass, right? And in this case, obviously, the acceleration is gravity, right? Because your weight is based upon the acceleration due to gravity on whatever planet you happen to be on, most likely probably Earth, unless you're an astronaut, one of the few who make it to the moon. Now, most bathroom scales are calibrated against this 9.81 meters per second squared, and they know how much force is being impressed upon them. And it's from that we're able to figure out our mass. Now this seems to indicate that an object's mass will determine how much a 100 Newton force will accelerate it. And obviously that has to be true, right? If you were to apply a force of 100 newtons to a mass of 100 kilograms, it would accelerate only a little bit, right? So if force equals mass times acceleration, and we want to isolate for the acceleration, right? Force over mass equals acceleration. Now what that means is if we applied a force of, say, 100 newtons to a mass of 100 kilograms, like if you picked up a really big rock and it was over 200 pounds, right? A literal boulder. And you applied a force of 100 newtons to it with, you know, a catapult or something like that, or a lever, I don't know, then you would be able to accelerate it at 1 meter per second squared, or about a tenth of gravity. However, if you applied the same force, 100 newtons, to a mass of 1 kilogram, it would accelerate at 100 meters per second squared, or 10 times that of gravity, right? So let's say you went out and found a rock that was 2.2 pounds, right? 1 kilogram. And you put that in your catapult, it would launch it really far, right? Whereas if you put a 200-pound rock into the catapult, it wouldn't launch it nearly as far, right? It would not accelerate it nearly as much. Now I've also included a link to a catapult demonstration video. Please go ahead and give that a look if you have not already. In any case, from this version, the acceleration is force divided by mass version of Newton's second law, we can see that the more massive an object is, the harder it's going to be to accelerate, right? It's a lot harder to push a huge boulder than it is to throw a small pebble. You could also say that the acceleration of an object depends on the ratio of the total force on an object to its mass. Right? Now, I want you to imagine a completely different scenario. Let's say there's some object, like a box of Christmas tree ornaments or something like that, okay? And you decide that you want to try to push it across the floor, right? So you're going to apply a force of, I don't know, say 20 newtons, okay? Now, what other forces are acting on this thing? Obviously gravity is acting on it, right? The weight, right? Mass times gravity. Obviously also the normal force is going to be acting upward, right? Because this object is neither flying up into space or falling through the earth. So these two have to be equal in magnitude and opposite in direction. Let's say there's also a frictional force that is slowing this down, right? You push, friction is going to resist. Let's say that the frictional force is something like 10 newtons. Okay? These two add up to 0. This one is 20 newtons, this one is 10 newtons. So that means if we were to try to account for all of these, the net force is 10 newtons this way, right? Now, if this object had a mass of 10 kilograms, what is the acceleration on this object? Well, let us consider our relevant theory. Force equals mass times acceleration. We want to isolate for the acceleration. So we're going to say force over mass equals acceleration. The net force on this object, we said, was 10 newtons. The mass of the object is 10 kilograms. 10 divided by 10, even I can do that one, right? So your acceleration is going to be 1 meter per second squared. It's not that bad, right? We should have an acceleration, therefore, of about 1 meter per second squared. Now, the force of friction deserves some special kind of attention. Like I said, let's say we're pushing this box of Christmas tree ornaments across the floor, right? And if you think about trying to move something across a surface, some big heavy thing, think about trying to push some really, really massive object or some bulky, goofy object, right? Something that's going to take a little bit of effort to try to push it. If you try to push this box across, say, a carpeted floor, you're going to have to overcome the force of friction first, right? It doesn't just effortlessly move. You can't just like sneeze on it or whatever, look at it really mean and expect it to move, right? You have to apply some serious force. But once you get the object moving, it's not as difficult, right? Why is that? Well, it just so happens that if we were, I'm going to redraw the situation just a little bit neater here. So here's our, obviously we have the weight and the normal force, those cancel out, right? Now we're going to apply a force to try to move this box across the floor. Force of friction is going to resist, right? And if we looked at just this little area here, you know, and blew it up, you wouldn't see two smooth surfaces, right? You're talking about carpet, right? So it's got a bunch of like uneven cloth woven kind of some kind of surface, right? And then you have a cardboard box or whatever it is in. And if you were to blow this up to microscopic, or blow up this tiny little microscopic area and have a really good look at it under a microscope or something, you would see that the cardboard box isn't exactly perfectly flat either. Now, if this cardboard box sits there for a little while, the irregularities in the cardboard box are going to intermingle and mesh together with the irregularities of the carpet, right? And so if this thing sits for any period of time, it's going to be harder to move it. But once it starts moving, these two are going to be separated some, right? It's not going to have time to settle. And so it's easier to move it once it's already started moving. This is the difference between what we call static friction, when things are stuck together, and sliding friction or kinetic friction, when two surfaces are already moving past each other. Which one is greater? Well, obviously our static friction, or our mu sub s, right, our static friction is greater than our kinetic friction or sliding friction, whatever you want to call it. If you wanted to draw a graph, I'm going to move to the other side. If you wanted to draw a graph of the strength of the force of friction, obviously in newtons, with respect to how much force you have to apply, you're going to have to push harder and harder and harder and harder, right, until all of a sudden it starts to move, and then you don't have to apply as much force after that. Makes a lot of sense, right? Now, what does the force of friction depend on? It just so happens that the force of friction depends upon the normal force. And if you think about it for a second, friction obviously only happens when two objects, surfaces come into contact, right? Now, if there's not a lot of force pushing the two surfaces together, there's not a lot of friction, like when the hands don't touch, right? But if you're actually making contact, right, the more force there is pushing these things together, the more friction there is. The greater the normal force, the greater the force of friction. And as a matter of fact, we usually say that the force of friction, which is also just sometimes written like this, say the force of friction is equal to the coefficient of friction times the normal force. Now, this coefficient of friction is basically a representation of the contact surfaces, the surfaces in contact, right? Like this would be really high if you were talking about concrete or asphalt, you know, the things that roads are made out of, and like the rubber on your tires. And the reason for that obviously is that we don't want people slipping and sliding all over the road and crashing into things, right? So you want the amount of friction in between your tires and the road to be very high. But the amount of friction between, say, steel and ice is pretty low, and that's why you can go ice skating, right? If there is no contact force, no normal force, there can be no friction. Makes a lot of sense, right? Which is why, if you do this, we're going to take, you can do this at home if you want to use like a coin or something like that, but I'm going to take this button and I'm going to put it here on top of this book. And I'm going to lift it and lift it and lift it, and eventually it starts to move, right? Why did that happen? Well, if it's just flat, then the coin is just going to sit on the book, right? If it's horizontal, right, if the book is, the cover of the book is horizontal, you've got the weight pushing down and then the normal force pushing up, and they cancel out to nothing, right? But if there's some kind of incline, right, so here's our coin on the book. Obviously, the weight is going to push straight down, right? Gravity always does that. There will be one component that is going to go into the surface of the book. And there will be one component of this at 90 degrees to the component in the book that's going to accelerate it downward, right? We'll call this weight parallel, and we'll call this weight perpendicular. And these two pieces add up to this piece, right? Now, obviously, there is going to be a normal force that is going to be equal in magnitude and opposite in direction to the component of the object's weight that is perpendicular to the surface of the book or the ramp or what have you, right? And also, the force of friction is going to act opposite that. Now, as long as the force of friction is greater than the component of the weight that wants to push the coin or pin or whatever you have down the surface of the book, it's going to stay there. Like this is greater than horizontal, right? But it's not moving. But then if it goes too far, right, when this component outweighs the force of friction, it will begin to slide down the book. Let's think back very briefly to the steel ball and the wadded up piece of paper again. Why did gravity make them both accelerate? Why did gravity make them both accelerate at the same rate, even though they have different masses? And we'll come back to this in greater detail when we talk about gravity in Chapter 8. But suffice to say that gravity is the attractive force between two massive bodies, any two objects in the universe that have non-zero mass. Right? Only bodies that have mass attract each other via gravity. But if bodies are more massive, is the gravitational force greater? Consider, if you will, an asteroid orbiting the Earth at the same distance that the Moon orbits the Earth. And as long as the asteroid is just, an asteroid, not very big, what is going to have a greater effect on the Earth's tides? Well, the Moon, of course, right? Why? Because it's more massive. But if the Sun is more massive than the Moon, why doesn't the Sun have a greater effect on the Earth's tides? Well, because the Sun is much, much farther away than the Moon is from the Earth, right? Thus, as Newton contrived it, his law of universal gravitation looks something like this. The force of gravity is minus g, your first mass times your second mass divided by the distance between them squared. So let's say you wanted to figure out the gravitational attraction between the Earth and the Moon. You would have to know the distance between them, and you'd have to know the mass of the Earth and the mass of the Moon. And you would apply this formula to it, right? M1 could be the mass of the Earth, M2 could be the mass of the Moon, R could be the distance between them, and you could solve for the gravitational force. What does this really mean? Well, what it means is the more massive the objects are that are attracting each other, the greater the force of gravity is going to be in between these two objects. Therefore, the ball and the paper fell with the same acceleration because the force of gravity is greater on more massive objects. And then the Earth is much more massive than the paper, the ball, the asteroid, or even the Moon, right? Okay, moving on. You can have friction with more than just books, right? What if you have friction with the air? Like so. Call that air resistance, right? Air drag, air resistance, friction with the air, whatever you want to call it, can slow down an object in free fall, causing it to have an acceleration less than 9.81 meters per second squared. How, you may ask? Obviously, the friction with the air is applied to the falling body in the direction opposite gravity, right? And so in this case, for air resistance, you have your free body object, right? In this case, a piece of paper. Obviously, the weight is pushing down, and this time friction or air resistance is going to slow the object's descent, right? Slow its acceleration downward. Now, have you ever heard of the term terminal velocity? If you've ever gone skydiving before, you probably know what this means. Eventually, if you go faster and faster and faster as you are falling, this force of friction, this force of air resistance, will equal the force of gravity. The faster you fall, the more air particles you're going to collide with, and the more air drag or friction with the air, whatever you want to call it, air resistance you will experience. And eventually, the force of friction will equal your weight, and you will stop accelerating. They call this terminal velocity because at that point you cannot accelerate any faster. Now, terminal velocities for falling bodies are obviously very different. If you wanted to consider, say, a steel ball and a wadded up piece of paper falling from a table, their falls are basically just the same. But what if you drop them from the top of the Empire State Building or something, right? They begin to fall together, but after they gain some speed, they would start to encounter air resistance, right? Now, the amount of air resistance that they're going to encounter depends on how fast they're moving, right, and how much air they come into contact with. But as they both encounter some air resistance, which one is going to slow down more? Well, remember, acceleration is force over mass. And if they're moving at the same speed with the same cross-sectional surface area, they should experience the same amount of force, air resistance, air drag, whatever you want to call it, right? And so the one with the lesser mass is going to have its acceleration changed by the air resistance more, right? Thus, the steel ball should accelerate towards the ground faster, and the air resistance should slow it less than if you dropped a paper ball the same size as the steel ball. I have included, of course, a video showcasing objects falling at the same rates and at different rates with air resistance. Please go ahead and take the time to have a look now, and I'll see you next time for Chapter 5.